Our next speaker is Stuart Weiss, a key scientist of the Creekside Center for Earth Observation. I don't know that we do CNPS conferences without Stu coming, just, you're here every time, always has interesting stuff to say. So we're glad to have him back. Thank you so much.
I love this conference. You are my people. And so what I'm going to try to do today is give you a deeper understanding, or any understanding, of this term climatic water deficit. So we're going to go off into the realm of watershed hydrology. And I'm going to show an example, just a sort of conceptual example of what the potential future of redwoods might be, because they love it wet, and California is going to be getting a lot more effectively dry. So in order to do this, we have to downscale global climate models. I'm not going to go into the details of this. GCM output is like a fine-scale GCM has a resolution of about a degree of latitude and longitude, and we have to get that down to a scale that's much more appropriate. So those are downscaled to a few kilometers, like 12-kilometer grid, then take it from 12 kilometer down to 270 meters. This is work by Alan and Lori Flint of USGS. So now we have like the 270 meter grids of temperatures and precipitation on a monthly basis across California, and now we're getting it across the entire Southwest. So here's what a map looks like at a 270 meter scale. This is our winter minimum temperatures. San Francisco's really mild in the winter, and as we go inland, it gets colder. We see the effects of cold air drainage in places like the Livermore Valley, where we get the inversions. Then we can see like the top of Mount Hamilton at about 4,000 feet is colder, but it's a pretty sharp gradient. In the summertime, it's like an exact opposite gradient. It's very cool at the coast. It's about 15 degrees Celsius at the tip of Point Reyes. Go inland about 100 kilometers. We're up in the mid-30s in Celsius. Very, very sharp gradient, and you can start seeing a lot of the detail based on elevation and exposure to the coast at this 270 meter scale. And of course, the fog is the big question mark. I will say my wife works for USGS, Alicia Torregrosa, and she is pursuing the fog. And there's a lot of exciting things that are going to be coming out in the next few years on fog. No, have to leave it at that. Really sharp precipitation gradients. We have 2,000 millimeters up here in the Sonoma Coast Range, some real wet spots in the Santa Cruz Mountains, and we get down to 250 to 300 millimeters at the inner part of the Coast Range. So the Bay Area is like a climate potpourri with intersecting climate gradients that don't always go in the same direction. So what do we do with this? Well, it's all about the water. So this is a watershed bathtub model. We get inputs of precipitation. There's soil storage, so like a big sponge inside the bathtub. Some water evaporates. When the sponge fills up, we start getting groundwater recharge. And then any excess water runs off on the surface as stream flow. So that's like the image that we're looking at. This is like a unit of soil that is collecting water, storing it, and sending it off, either recharge or runoff or evapotranspiration. So we can start making equations out of it. Water is conserved, so inputs equal outputs, and the difference between the inputs and the outputs is the amount of soil storage. So then we take the simple bathtub model, we can program it in the language Fortran. That's Alan's specialty. He's an old-time scientific programmer. This is Alan and Lori Flint, who many of us owe an incredible debt to. And the ecological and conservation community discovered them about 6 or 7 years ago, and it's been really fruitful. So this is what the structure of the model is. We have inputs of precipitation, solar radiation, and temperature. Calculate potential evapotranspiration, and that is the evaporative power of the atmosphere. That's how much water you could evaporate if it were freely available. Really important term. Then you have how much watershed available water there is when you take out the amount of evapotranspiration. And that goes into the soil profile. Soils have a certain water holding capacity. That gets filled up. There are fractures below. Some soils are very poor, some bedrock is very fractured, other bedrock has very little fracture. It makes a huge difference in whether water goes to recharge or runoff. We transpire out of the soil, and then there's this mysterious term, the climatic water deficit, which is the difference between the potential evapotranspiration and the actual evapotranspiration. And you can think of it, that's water that's not there. Now, a lot of people ask me, well, how do you know their model's any good? They're like the best hydrologists in the world, and they calibrate it really carefully to unimpaired stream flow. So you know you're getting the water balance more or less right at a watershed scale. And it's based on really straightforward physical principles. And it shows the behavior of systems that we can recognize. So it's by far the best thing we have going at a wall-to-wall coverage. So these are the terms. We have soil storage, that's the available water in the rooting zone, soil type specific. We have recharge, which is water that goes below the rooting zone into shallow and deep groundwater, and that depends on the permeability of the bedrock. The runoff is the excess water that runs off on the surface. The potential evapotranspiration is the atmospheric water demand. We have the actual evapotranspiration, which is how much water is actually evaporated because it depends on the availability of the water. And that's how much is used by the vegetation use. And it's a really good first order estimate of vegetation productivity. The more water used by the vegetation, the more photosynthesis takes place, the more biomass you can have. And then this climatic water deficit is the difference between the potential evapotranspiration and the actual evapotranspiration. You can think of it as water that's not there to be used, and it's a good integrated measure of seasonal water stress. So once again, the physiognomy and composition of California vegetation is really constrained by drought stress. We're in a Mediterranean climate. The intensity of the dry season is really, really key. And CWD is a TLA. It's a 3-letter acronym. I use those a lot. AET, that's a TLA too. It's an integrated measure of seasonal drought stress, and it takes 36 monthly values of Tmin, Tmax, and precipitation, and it turns it into one number. It's a lot easier to do statistics when you have one number as opposed to when you're fishing around among 36. It includes soil moisture holding capacity and a topographic correction for insolation at that 270 meter scale. So we're picking up the big north versus south slopes. So a lot of topographic variability and nooks and crannies below that, and I'll talk about that a little later. And there have been numerous studies that are finding the value of CWD for predicting tree death, recruitment, and performance. So I'm going to take you through a water year. This is Pine Gulch Creek and Point Reyes. This is our water balance diagram that we should try to show the dynamics. The water year goes from October to September. So in 2006, we got a little bit of precipitation in October, about 25 millimeters, went into the soil, evaporated out again, and it did not meet the evaporative demand, so there's this climatic water deficit we have here. November, we got more precipitation, we met the potential evapotranspiration, we stored some in the soil. December was a really big month this year, and we filled up the soil column, so now we're like full soil storage, generating recharge, a lot of runoff, and then we have some evapotranspiration. That's not that great because this is the cold time of the year and there's not much atmospheric water demand. Get a little less precip in January, another pulse in February, and then we can start seeing that the AET is increasing because temperatures are going up and the ability to evaporate water is going up. Then the rainy season, we got a lot of rainfall in April of this year. And then the rains stop, we get all this actual evapotranspiration, it draws down the soil so that soil moisture just drops close to zero, and then we're not meeting the evaporative demand here. So in June, we could only evaporate off about 25 or 50 millimeters of water. There's over 100 millimeters of unmet demand. So when I talk about annual climatic water deficit, we're basically looking at this red area during the dry season. Does everybody have that? Okay. So this was a good wet year. The total CWD was 594 millimeters in this watershed, and there was 549 millimeters of actual evapotranspiration. This is a very productive site. We go to the next year, this is 2007, which was the fourth driest year since 1895 up to this date. Lot less precipitation, so we're not generating very much recharge and runoff. We barely fill up the soil column, and then a lot of actual evapotranspiration in April, and the soil is drawn down, and we end up with a much bigger area of climatic water deficit. So here the CWD is 739 versus 594, and that's a big difference. So then if we take 30 of these years, we create what is really the weirdest weather year you could ever find in California, one that is average every month. So this is a climatology, it's a hydroclimatology showing how this watershed behaves on average over a 30-year period. So on average, 656 millimeters of climatic water deficit and 494 millimeters of actual evapotranspiration, and then it's generating runoff and recharge. And that's all out of 885 millimeters of precipitation. So that's sort of how the dynamic works in any given year. Now we can look at climate change. So what I've done here is, this is Fern Creek, slightly different watershed close by, for 1981 to 2010. So this is our kind of baseline recent average. This is at the end of the century under this GFDL A2, which is a high emission scenario and a drier model. You can see there's less water available, and the shape has changed a little bit, and this red area is considerably larger than it is here. This is a different future that's actually wetter, but notice that the increased precipitation is coming in mid-winter, where it goes to runoff and recharge. It's not available to the plants, and we still get an increase in climatic water deficit. So under the GFDL A2, we have a 219 millimeter decrease in precipitation, a 144 millimeter increase in climatic water deficit. That's like an increased demand of about 6 inches of water, which is a lot that needs to get met. Our AET goes down a bit. Under the wetter scenario, CWD goes up to 60, and even though it's wetter, AET actually goes down a little bit because the rainy season is being compressed and more water is going off as recharge and runoff, which is, makes the water managers really happy, but the plants, it's gone. So now we can, let's look at the evolution through time. So here's the historic period up to this line here. The light gray is the annual values. The blue line is the 3-year running average. The red line is a 10-year running average. Because we know we can get through one dry year. 3 dry years starts really stressing things out. And then when you have a long-term 10-year stress, So historically, CWD has been going up because with the historic climate change in the last 30 years. We can see that the maximum 10-year running average was here in the mid-90s. The maximum 3-year was here in, I think it was 1990. And then we start going up into the future. So here's this relentless rise in CWD because it's getting warmer, and in this case, we're getting less precipitation. We start seeing these exceedances of the 3-year running average, and then we get out to the end of the century. In this particular future, all climate futures are wrong, but we use them to see sort of what level of stress we're going to see in the system. This produces a mega-drought at the end of the century, just so far in exceedance of any historical values. But we see that we start exceeding the 10-year value about 2030 is when we've exceeded the historical maximum value, and it just keeps going up. Under the wetter future, we go up. We start to do the exceedance at about 2040 and go up. So now I'm just going to do a real quick. So here's the map of CWD in the Bay Area current period. Here's at the end of the century. So notice how this yellow out in the Central Valley. Okay, so the water stress we'll be seeing in a lot of these areas here is going to be equivalent to what we're currently seeing at the fringe of the Central Valley. And that's aridification and xerification. We can take a look at a particular vegetation type. So this is the last thing I'm going to show here. We look at the distribution of mapped redwood forest, which is the blue and the red here. And we do this across the whole Bay Area. This is just a section of Marin County. And we just see what's the distribution of CWD values. So we see that 90% of the current redwood forests are below 800 millimeters. We go out into this GFDL A2 future at the end of the century. We see that only 25% of the current distribution of redwoods is below 800 millimeters. And when we look at where redwoods are going to be really water stressed and potentially die, that's all the red areas here. Now the red areas are what we call the trailing edge. It takes a lot to kill a redwood tree, I agree, and that's why we're looking at an end of century. But there's still some blue areas out here in the nooks and crannies of the landscape where there will still be some small stands of redwoods in Marin County. So we're maintaining a biogeographic distribution, but we're going to potentially lose a large fraction of the current distribution. So moving forward, these two, CWD and ET, are major determinants of vegetation physiognomy and composition because it really is all about the water. CWD always increases with warming because we have this limitation of soil moisture holding capacity. We're going to be developing these trailing edge maps in the Bay Area for all appropriate vegetation types, and that's where the existing vegetation is already on its edge and is most vulnerable. And the BCM, the Flint's model, is a major platform for climate change assessment in California and the Southwest because we're turning climate into hydrology, and that's what really matters. So thank you.
We have time for one question.